Okay, let's go. So we're going to finish Euclid today. We're going to finish off Euclid. We had a lot of EUs, right? The Eulers and Euclid. Okay, we're going to do some bijection, CRT, and isomorphism. We're going to talk about these concepts again. And we're going to do Fermat's little theorem. Okay? Okay, so last time we showed how to efficiently tell if there is an inverse. And we started to do this extended Euclid's, the proof of the extended Euclid's theorem to find an inverse. Okay? So remember, just to remind you, this is the GCD algorithm. Really what you do is you basically, it's just recursive. You take GCD of xy, and then you take GCD of smaller things, right? Y and mod xy. And the mod xy is really, you can think of it almost, you might as well think of it as x minus y. It would work, my analysis worked for x minus y. Okay? So the switching is just something to keep the invariant that the first argument is largest. Okay? So it computes the GCD of x and y in O of n divisions. Now n is not, now we have two notions of size of a number. Its value and the number of bits to represent it. Okay, so here it's the number of bits for an integer. Okay, this n is basically, and this relationship is roughly n is equal to log base 2 of x. Okay, if you're using base 10, it would be log base 10 of x, roughly. Okay, so for any x and m, if GCD of x and m is 1, then x has an inverse. We proved that using a bijection. Remember, we said, look, we did this map from f to f of a is x times a, and then we argued every element of that range is different, and therefore one of the elements of the range must be 1, and therefore there's an inverse, right? You all remember this proof, right? Perfectly. The midterm's coming. You understand this proof, right? Good. Okay. So, So GCD algorithm used to tell if there is a multiplicative inverse. How do we find a multiplicative inverse? So this is, we started, did I miss one? Okay. So this is extended GCD algorithm. I think I skipped 2 slides. I meant to skip 1 slide from last time. But let's just do it. Okay. We're going to go fly without the warm up. Okay. Okay. This is almost like the GCD algorithm, right? Last time we just returned one thing. Now, I really need the multiplicative inverse. Sorry, I left out a slide that really needs to be there. Okay. Okay, so let's see. Please. Did I get the right one? No. Okay, did I get the right one? Did I save it? No changes need to be saved. Okay, so sorry. Okay, this is the extended GCD theorem. AX plus BY is equal to D, where D equals GCD of X and Y. That's what we're saying. We're saying that we're taking the numbers X and Y. We can add and subtract them, right? No matter how we add and subtract them, whatever this form is, no matter what integers we use, AX plus BY, it's going to be a multiple of D. We're just sunk on that. We know we have to be a multiple of D. Right? Any expression ax plus by, if x and y are both multiples of d, ax plus by is a multiple of d. But this says I can actually set up integers a and b such that it's the smallest possible multiple of d, other than 0. Okay? Okay, does that make sense? Okay. So make d, you're making the greatest common divisor, out of the sum of multiples of x and y. Okay. Now, we said last time, what is the multiplicative inverse of x and m? Okay, so now what we're going to do is we're going to take the GCD of x and m, and we know that it's 1 because it has an inverse. Since it has an inverse, we know that ax plus bm is equal to 1, and we know that ax is equal to 1 minus bm, right? We could just do arithmetic, and we see that. And the mod m, where'd the bm go? The b times m? B times m mod m is 0. Okay? Okay, so A is then, we have something that when you multiply by x, you get 1. So that something must be the multiplicative inverse of x. Okay, by definition. So for x equals 12 and y equals 35, GCD of 12 and 35 is 1. Do you see how to add and subtract them to get 1? You see how to add and subtract them to get 1? Multiples of 12 and plus or minus some multiple of 35? Yeah, 3 times 12 minus 35, right? That works. 3 times 12 minus 35. Okay? 3 times 12 times negative 1 times 35. Is that clear? And it equals 1. So the game here is try to figure out these A and B. Here A and B are 3 and negative 1. There's probably other solutions, but this works. There's lots of solutions, in fact. Okay, so what's the multiplicative inverse of 12 mod 35? Oh, right. Do you see that? It's A. A is 3 and B equals negative 1. We said it was A back there. Okay, right? And do you see why? 3 times 12 is 26, which is equal to 1 mod 35. Okay. Excellent. Okay, so now we're going to do an algorithm, right? It looks like GCD, except it got a little messier, right? We put the x dash in. It's still in scheme, so that part's still beautiful. There's the x dash. Does scheme allow you to have a dash in the middle of the name? Maybe not. Okay. I should have compiled it. Or run it. Okay, so sort of, no, it isn't scheme. It's something else. I don't know what it is. Okay, so DAB is equal to this recursive call. So now each of the things are going to return 3 things. Okay? The first thing is the GCD of A and B. And what we want the second 2 numbers to do is A times the first argument, which is x, plus b times the second argument, which is y, should equal d. Okay? It's just a procedure. This is it, right? And we said we want, so when we're given x and y, we want to know 3 things. The GCD and a and b, where a times x plus b times y is equal to the GCD. Yeah. Yeah. Yeah, it's supposed to say GCD of x and y. Okay, that's okay. Well, okay, GCD of x. I'm tempted to get in there. Okay, sorry. Okay, should I do it? You want me to do it? Okay, no. Okay, so okay, let's just run it. Let's see what it's doing. The weird thing is here, right? But you can sort of see the 2 things. There's the floor of x and y. It's some sort of weird number, and then mod of x and y. And so, you know the mod of x and y is in floor, uses floor of x and y. Right? Remember that? When you want to take the remainder of something, you divide, you get the quotient, and then you subtract that quotient times the thing you're dividing by. Okay. So 35, 12. What's the first calls we do? What we do is we take 35 mod 12, and put it in the second position. That's what we're doing there. And we switch the y into the first position. Okay, that's what we do. And then the next time we take 12 mod 11 and put it in the second position, and take 11 and just copy the second number over to the first number. So that's what we do on the way down. It's the same as before. And eventually you do the same thing. 11 mod 1 is 0. Everything mod 1 is 0. So you get a 0 there and 1. Okay, I'm just taking this mod for the second argument and copying the first argument over. Okay? Okay, so now let's think what we do on the return. Okay, so what we do in this base case is we return x, 1, 0. So this last call we got a 1 was x, so we return x and then 1, 0. Okay? So now we notice that this equation is satisfied, right? The GCD, the first argument, is equal to the second argument times, the first return value is equal to the second return value times the first argument, plus the second return argument value times the second argument. Okay? So we have the condition. This is the claim. So for this last call, we're verifying that the claim holds. Right? You see, that's what the blue on the right is doing. Okay? So now what you do here is in this return, what do? So this next return, you got 1, 1, 0. So this first line here got 1, 1, 0. So what we're going to do here is we'll return 1, we'll return B, that's 1, 0 in this case, and return A minus the floor of xy times B. Okay? So that's what we're doing here, and I guess that's 1. And so look, does this equation get satisfied? Yes. Right? And not only is it satisfied, is it the right equation? So we were supposed to look at 11. 11 is supposed to be multiplied by our first value, and the second value is supposed to be multiplied by the second return value. Okay? So what we're doing here is we've changed this equation. We changed the right-hand side here, and we basically plugged in different x and y's, right? But what we did is we said, look, 11 came from 1 somehow, and we're reconstructing it. Okay? So that's what we're doing here. 1 we kept. Okay, yeah. Okay, and so on. You can come back and you can see now this equation is finding a solution to 1 equals some multiple of the input arguments. Some multiple addition and an additive function of the input arguments. And finally you get this. Okay? And all of this is just sort of backing out the equation. I'm just running it. All of the calculations are there. Okay? Okay, so really this is a weird thing. Why are we doing that? Okay? Well, because in some sense that's what we did on the way down. Okay? To build D. To build the arguments. The next arguments we use this argument here, this mod, is built on the way down from x and y in some way. And now we're trying to get it back. Get back x and y. Or get back x, in fact. Okay? So here's the proof. Okay. So the theorem is it returns DAB, where D equals GCD of x and y, and D equals AX plus BY. Okay. So the correctness is just induction, or I guess we're saying strong induction, but to me it's induction at this point. Extend the GCD of x and 0 returns D equals x1, 0. So it returns a tuple x and 1 and 0. And here for x and 0, what is the GCD? That's the first thing we need to remember. It's x. The GCD of x, so that's correct, because that's what it's returning, x, which is the GCD. And this equation is satisfied, right? X equals 1 times x and 0 times y. Y is 0, so whatever would work there. So the base case works. Now we're going to return D times, I'm just changing the letters because it gets a little confusing which letters are going to be in the recursive call and which ones are in the higher level. Okay? So I'm going to say at the induction step is it returns something, D, A, B, and with D, A, X plus B, Y. Okay? So now what it says, that's what we need to prove. We need to prove this, that what is returned by the procedure it satisfies this equation. Okay? That it returns D and A and B, and our inputs are X and Y. So D should be A times X plus B times Y. Right? Okay. So we can assume by an inductive hypothesis that that the extended GCD on these smaller values, Y mod XY, returns D, A, B, right? And it satisfies this equation with D equals A times Y, because now Y is the first argument, and B times the second argument, which is mod XY. Okay? Okay. So D equals that. We're going to use induction hypothesis right away. Okay, now do you see what to do? What is that mod xy? That's weird. Let's get rid of it, right? Let's try to write it in a different way. Okay? What if we write it that way? Okay, now what do we want to do? We want to write down a right-hand side here that's something times y and something times x. Do you see how to do that? Yeah, you just factor out, reorganize, or multiply through and reorganize, right? So this is exactly what we return, right? So now I've reorganized. I've taken everything that multiplies y and put it together and added it up, right? There's an a times y. There's a b times the floor of x over y times y, a negative. So that I put that in this parentheses, and I put b times x in the first parentheses. Over here. So, okay? So that is exactly what the extended GCD returns. It returns what it gets from the first guy, right? It returns b, okay? And then it returns a times the floor of x divided by y times b. Okay, so that's what it returns. And so therefore, and if it returns these two, we see that this equation is satisfied by induction. Okay? Okay. I should maybe put that line first. Okay? If, here we can see it again here. Here's DAB. You get that back from the recursive call. And then what you return is D. B now multiplies the first argument, and a minus 4x times y will multiply the second argument, right? So that says that D equals A. This is what we do return, right? We return D times B times this floor. That's this expression here. And now I'm checking this equation. So it's saying that D equals this. This is what I'm using inductively. And I'm just reorganizing, and I say D equals this expression, and now that's exactly what's returned, right? These this, and this. Okay, so it's fairly simple. Okay, so that's all fine, but there's I don't know. This is the way it's done in the notes. It's okay, but to calculate these things, it's a pain using. You're not a computer program. Yeah, you will be replaced by one soon, but not yet. So it's not that easy. For them, it would actually be easy to do this, but this is a big pain, right? So let's think of what we're really doing. Another way you could actually prove it this way. Okay, so let's think about what we want to do. We want to do the GCD for this one is 1. So what we want to do is we want to express 1 as some multiple of 7 times some multiple of 60. Right? So here's two equations. The first equation is definitely it's some multiple of 60, and plus some multiple of 7. Not a very interesting multiple of 7, but it is, right? And 7 times 1 plus 60 times 0 is 7. Okay? So what I want to do is these equations do what I want, except the right-hand side is not correct. We want them to be 1. They have the property I want. Okay? So what should I do to make the right-hand side closer to 1? Can I add these equations? If I add these equations, will the left-hand side still be sums of multiples of 60 and multiples of 7? Right? There'll still be sums of multiples of 60 and so I can add these equations, or I could do something else. I could do this really fancy thing. I could subtract these equations. Okay, I can even multiply them by something and subtract. Right? Here I multiplied by what? I multiplied the second one by 8, right? And I subtracted that equation from the first equation. And what do I get? I get 7 times negative 8. I'm leaving it factored over here. I'm just writing the coefficients of 7 and the coefficients of 60. Okay? And 60 times 1 minus 0 is 60. Okay? Then what do? I subtract again. Now I subtracted the third from the second. I just subtract it and multiply, and then I get these new coefficients, right? The -8 becomes a positive. I get a 9. It's always hard to keep track, but then I get this, right? Fairly easy. This is an easier way to calculate these things. And one can do a proof based on this too, adding equations. It's essentially the same thing. It's taking the downward thing and the upward thing together. It's just doing them together. It's just keeping track on the way down in some sense. You can make it a tail recursive algorithm. Okay, so let's confirm. This is a confirmation. It seems to work. So good. Okay. So okay. So the conclusion here is that with this algorithm, we're going to give you sequences of algorithms and theorems to give you some structure of number theory, and then we're going to use it to build public key cryptography. So here what we've done is we've given you an efficient way to find multiplicative inverse modulo mod m. Okay? Okay, it's very different, and we did something, right? We didn't do nothing. We actually, the stupid algorithm is really, like, it's not clear there's a better algorithm a priori. This is how much better. It's like, say, you take the inverse of this big, it's only a 9-digit number, modulo this 10-digit number. That would, 80 divisions using GCD versus 1 million using these things. But in internet security, when public key cryptography, you have about 500 digits. So it's 500 divisions versus this many divisions. And this many divisions is a lot of divisions because there's a little 5 there. That's not a footnote. That's 2 to the 5th power. So it's a lot. Okay, so it's a lot more efficient. Okay, so let's start building a couple of more number theory tools. We'll look at this thing called the Chinese remainder theorem, which is and Fermat's theorem. Okay, but before we talk about that, I'm going to go back to bijections just quickly because it's really critical in a lot of these arguments. Okay, so bijection is 1-to-1 and on-to. Okay, so f of a to b. Sometimes they call it domain and codomain. So versus range. The range technically is what they actually hit, right? So there's some confusion, but just ask if you have any confusion. Sin x, a and b are the reals. The range is -1 to 1. And it's onto -1 to 1, but it's not 1 to 1. Right? So sine of pi is equal to sine of 2 pi. No, sine of 0 is equal to sine of 2 pi. Right? Does that make sense? Well, actually, technically, sine of pi is equal to 2 pi too, but well. But if you add 2 pi, you're going to get the same value again. Right. Okay. The range definition is always onto. Okay? So that's what I'm saying. When people say range, they mean something else. But it's not 1-to-1 here. Okay, consider this. Now we're going to go back to modular arithmetic. When is this function a bijection? Okay? You just have to figure out which two things to take the GCD of. So the function is a times x, right? So we know that if a and m, their GCD is 1, what does a have? Multiplicative inverse, right? So that means you have a bijection, right? If you have a multiplicative inverse, you have to have a bijection, because if it's not a bijection, if two people go to the same place and you have an inverse function, then you don't know where to send them back to. So it's 1-to-1. Okay? Now why is it onto? Because the domain and the codomain are the same size. They're all the elements from 0 to m-1 are their equivalence classes. Okay? So the codomain and the domain are 0 to m-1, and it's a bijection when GCD of a and m is 1. Right? That's a not example. An example of a not a bijection. If a equals 2 and m equals 4, then f of 0 is both 0 and 2 both map to the same element in the range. Right? So there's no inverse function from 0. You don't know where you came from here. Okay? So the inverse function of f of x equals ax is a inverse x, right? If you say a inverse of a times x, you get back x. Okay. Okay, so lots of mods. Okay, let's do a lot of mods. I think that's a long ago joke about quadrophenia, but you don't know what that is. So who's ever heard of quadrophenia? Oh my. It's a great movie. You should see it. There's the rockers and there's the mods, and they kind of are like these British gangs, and they kind of fight each other a little bit. And the mods go around. We are the mods. We are the mods. Okay. Well, never mind. It's all it's fun. It was fun. I like the movie. And the album. It's by the Who. Where was I? Okay. What is x mod 35? So there's some x. Now I'm saying something different. Now I'm thinking in this realm where x is not from 0 to 4. It's just some number, some integer. Okay? Now, the equivalence class, when I'm using this equation x equals 5 mod 7, I'm saying the equivalence class that this number belongs to is the 5 equivalence class mod 7. So it could be 5, it could be 5 plus 7, which is 12, and so on. Okay? We don't know what it is. It's some integer. Okay? And x equals 3 is some integer as well, and it's in the equivalence class that is 3 mod 5, which is 3 and 8 and so on. Now, we say if we have these two things, these two conditions, x equals 5 and x equals 3, what is x in some sense? And what we want what kind of x we want is the mod 35, which is it's sort of the multiple of it is a multiple of 7 and 5. Okay, so let's see what it is. I mean, is there even something that x mod 35 is also something that's x that's say 7 mod 35 is also 5 mod 7 and 3 mod 5? Okay, so not 3. Let's try 3. Let's just do our stupid algorithm. So 3 doesn't work. Okay, 3 mod 5 is not 7 mod 5. Right? Let's try 5. 5 is not 3 mod 5. Let's try 3. 3 is not 5 mod 7, right? So we're just trying the numbers that we see. It's sort of a dumb algorithm. Oh, there's a 5 there, there's a 3 there. Let's try them. Okay? Okay, so now let's try a little bit harder. Okay, so now if x equals 5 mod 7, if you think about all the ranges, all the numbers in this arithmetic system mod 35, this is it. These representatives represent them all. Okay, 5, 12, 19, 26, 33. Okay, so do you see which one is 3 mod 5? Is one of them 3 mod 5? 33 is 3 mod 5, right? Did anybody see that? You saw it. Well, you saw the mistakes on my slide, so I don't know. Yeah, about you. But okay, yeah. So, okay. Yeah, there's only one solution, right? Do you see 2 solutions? So that's kind of nice, right? There's only one solution. There is one solution, and there is two solutions. There's not 2 solutions. So it seems like maybe it's a bijection, right? Maybe this sort of representation where we take x equals something mod 7 and x equals something mod 5. There's exactly one guy mod 35, which is sort of satisfies these 2 equations. Okay. Okay. So there's a poem there. My love is 1, 0 and 1, nothing and nothing done. Okay. So what does that mean? Okay. So it means I like something. Yeah. Okay. I like 0 and 1. Okay. 0 and 1 are nice. Because 0 is nothing, and when you multiply by 1, nothing happens. Okay, that's the deep analysis of the text. Okay. It's a big deal, 0 and 1. 0 and 1 are really like big deals, okay? They really are, okay? So they do things and they're big deals partially for what I said. Okay, so x equals a mod m, x equals b mod n, where GCD of m and n is 1. That's what we had before, right? The GCD of 7 and 5 were 1. Okay, and we had x was 5 and mod 3 mod 5 and 5 mod 7. Okay, but that was the example. Okay, now I want to say there's a unique solution to x mod mn. Okay? And, okay. So I'm just going to construct it. Okay? Because the poem told me to. It told me to, like, construct 0 and 1 somehow. Okay? So this is what I'm doing. N inverse, if I was mod n, what would that be? N times n inverse. If I was mod wait. So let's just do this. So 0, it's 0 mod n, right? Do you see that? Why is it 0 mod n? It's got a multiple of n in it, right? Now, n inverse looks like might be some weird fraction or something, but it's just an integer, right? It's some sort of integer. So u is equal to n times some integer. So if you take it mod n, what do you get? You get 0, right? So this thing u is, if I take it mod n, it's 0. Now, what if I take it mod m? What do I get? Well, I get some number mod m times its inverse mod m. What do we get when I multiply a number by its inverse? 1. Right? Yeah. Well, these are prime. Let me just make them prime for now. Yeah, they're primes. GCD of m and m is 1. Or wait. Just let me think for a second. They're primes, right? Because the GCD of everything with each other, right? So they're different primes, is what think of them that way. Okay, so I'm trying to think of something. They're primes. Okay. And now, look, this is 0 and 1, right? So these are nice, right? With 1, if I want to make, 0 and 1 are going to be really nice, okay? Because, I'll show you. Okay, so now you consider this one, and it's the same argument, right? If you take this mod m, what is it? If you take it mod n, what is it? Okay? If it's mod n, you're taking some number m mod n, you're taking this number m mod n, and then you're multiplying by the inverse mod n, which means it's 1. Okay? And now v equals 0 mod n, m, because it has a multiple of m in it. Okay? Okay, so now that I have u and v, can I construct x where x has these properties? X is equal to a mod m, and x equals b mod n. Okay? I'm going to show you in just a second. But just take a second and see if you think you might be able to do it. Right? The one thing is, okay, let's think about let's think of column, mod n. Okay? So there's u and v, right? We can use u and v. And what we want to do, mod n is we want it to be b, right? Does u help us mod n? Mod n? It's 0, right? And anything we do with u is not going to be very helpful. So we should multiply b times v. And that seems like at least it'll get us right mod n. Okay? But now whatever we do to fix ourselves mod m, we could screw up. Except, look, there's a little help here because the other guy is 0 here, that mod n. So he won't screw you up. So really, you should just do this. Let's just look at it mod m. It says I should multiply a times u because I got a 1 here right? A times U is 1 mod M. Okay? And B times V is 1 mod N. Now, the problem is the other guys can mess you up, right? Because you don't only have B times V mod N, you also have A times U. But U is 0 mod N. And so on, right? So, let's do that again. X is equal to A times U, B times plus B times V. That's because B times V is equal to 0 mod M, and A times U is 1 mod M, so A times U is A. So what you get in this expression is A. So it's just a construction. And what about mod N? Well, A times U is 0 mod N, right? We can just look up here. And B times V is 1 mod N, right? B times V is B mod N. V is 1 mod N. B times 1 is B mod N. Okay? So is that the only, so that says, given A and B, I can find X. Okay? Okay? I just gave you a formula for doing it. Okay? Okay, this is X equals A times U plus B times V, where U and B are defined as in the poem, right? The poem has a really deeper meaning. It has this is the proof of the poem is referring to the proof. Okay? Okay. So if not, the rhyme, maybe it's too much to call it a poem. If not, two solutions X and Y, right? Okay, so we want to say there's a unique solution. We showed you a solution, so there's at least one. And now we want to show you there's not more than one. And we will do our standard thing. We'll take the difference between the two solutions. If the two solutions are both solutions to both equations, x minus y has to equal 0 mod m, and x minus y has to be 0 mod n. So in that case, what must x minus y be? It has to be a multiple of m and a multiple of n, right? Because it's 0 mod m, so it's a multiple of m. It's 0 mod n, so it's a multiple of n. Okay, so now x minus y is a multiple of both m and n. Now, that tells us that x times y, now these are relatively prime. So x minus y is bigger than m over m times n. Or it's 0. If it's 0, that means x and y are the same thing. Okay? But if x minus y, if they're different, if they're two different solutions, they have to be bigger than m times n, which means that x and y are not in this range. Okay? Okay. Okay, so that's the CRT theorem. It says there's only one solution to these two equations, mod m. Okay, that's you can do this for many equations, mod many primes, P1 through Pk. That's the general CRT theorem. It's the same proof. I mean, except that the notation is a lot messier. What you have is a bunch of zeros and one, and you have an n of them. Okay. Okay. So now that's one theorem. So there's this bijection between A and B pairs, mod n mod m, and x's mod n times m. That's what it says. Okay. So this is Fermat's theorem, Fermat's little theorem, not the big theorem. It wasn't his in the end, but for prime p and a not equal to 0 mod p, a to the p minus 1 is equal to 1 mod p. Okay. Okay. So this is okay. I don't know. It's a statement. It's like a little bit interesting, right? There's a pattern here. A to the p minus 1 is equal to 1. Okay? Okay, so that's... Because you do wrap around, right? Because everything is between 1 and 0 and p minus 1. So this is saying, when do you wrap around and hit 1? Okay? This is telling you how long it takes to wrap around in some sense. Okay? If you keep multiplying by a, p minus 1 times, you get back to where you started. Okay? So it's kind of cool. Okay, so what we're going to do is we're going to use this bijective proof. We're going to start with a, and we're going to multiply it by 1. We're going to think of a as a function, and we're going to multiply it by every element in our set other than 0. Okay, so the elements in our set here that we're talking about are 0 through p minus 1, and we multiply a by each one. So then we form a new set. A times 1, a times 2, and so on. Okay? All of them are different modulo p, right? Since A has an inverse mod p. Right? Okay, so this is sort of we're using the inverse property, and I sort of made the inverse proof in class be this bijective proof, right? Because the one in the notes is a bit different. But you should see this trick before, right? You just get this big range of numbers, and you say, well, they're all different. Okay. Now, what it says is if all these numbers are different, and what is the range of what is the codomain? Well, none of these numbers are 0. When you multiply two positive numbers, you don't get 0. Ever, right? But you might get a multiple of p, but you don't get a multiple of p, right? Because that would tell you it doesn't have an inverse, right? It goes to 0, right? It has an inverse. 0 doesn't have an inverse. Okay? Okay, so nothing times 0 will come back to our original set, which is 1 through p minus 1. Okay? So it says that the range is 1 through p minus 1. It's 1 to 1. So what is S? What is that? Instead of thinking of this ordering, that I have a particular ordering there, but S, the elements of S are exactly the same as the elements of 1 through p minus 1. Right? These are the same sets. S up there, a times 1, a times 2, a times 3, is also 1 through p minus 1 as sets. Right? So let's multiply them all together. They have to be equal, right? Because I'm multiplying all the elements of S together, and all the elements of 1 through 1, I'm multiplying 1 times 2 times 3 up to p minus 1. And they're the same sets. So I can multiply the elements of the right set together, and then multiply the elements of the left set together. I get the same values. Now, in this expression, they're in different orders, right? Because I'm multiplying a times 1, a times 2, a times 3. A times 2 is not 2. It's something. 2 is somewhere in this expression, but I don't know where it is. Okay? Okay, so but this equality holds. And now we just use commutativity of multiplication, right? We can switch around. The set, when you multiply things together, it doesn't matter what order they're in. You can switch them around. So that's what we do. We switch them all around. We factor A's all out to the front. Do you see something? Does something look the same to you on both sides? Can we get rid of that? Can we get rid of this big mess here and this big mess here? Right? Well, we can multiply by the multiplicative inverse of every one of the elements has a multiplicative inverse, so we can just take them all out. Okay? That's the proof. Okay? Does that make sense? Okay. So, in some sense, there's generalizations of this. You can do this any mod anything, and what you get is if you have something that's relatively prime to the modulus, you get a to the number of things that are relatively prime to the modulus. Right? In that case, the number of things that are relatively prime to p is p minus 1. Everything is relatively prime other than 0. Okay? So you can generalize this proof. Okay, so we can do some cool things. We saw that we could reduce with arithmetic or addition or multiplication in modular arithmetic. We could also reduce this exponent. So let's reduce this exponent. Let's do it this way. Okay, that's apparently the wrong way. What's wrong with that? I'm claiming here, I'm taking the exponent. Remember, when we reduce with arithmetic, we reduce all the numbers by taking the remainder mod 7. So I'm trying to do that with the exponent. Is that what Fermat's theorem says? Does Fermat's theorem say I could reduce that 2 to the 7 is 1? What does it say is 1? What is the modulus? 7. Right? If we plug in 7 here, the modulus is 7. It says for everything that's relatively prime to 7, 2 to the 6 is 1. Right? So this is wrong. This is sort of assuming that 2 to the 7 is 1. And that happens a lot. So I just wanted to show you that. So 2 is relatively prime to 7. So 2 to the 6 is equal to 1. So we could reduce the exponent this way. We can just factor out instead of multiplying 2 101 times, we can just get rid of anything that's sort of larger than p minus 1. Right? We can factor out, we can write it, just take the remainder mod 6 in the exponent, which is what I'm doing. And now I have 2 to the 5. And 2 to the 5, and now I only have to do 5 multiplications to get it, to get my answer. Okay? Okay, so that's what it says. We can reduce exponents modulo p minus 1. Right? So, okay, that's a quick thing. So we had a bijection, f of x equals ax mod m if GCD of a equals 1. Now, for a Chinese remainder theorem, we had a bijection from pairs of numbers mod m and mod n to a number mod m times n. Okay? So pairs of numbers, a mod n, b mod m, correspond to exactly 1x mod mn. That mn should be inside the parentheses. Okay? So for m equals 5 and n equals 9, if ab equals 3, 7, then 43 is the x mod 45 that it corresponds to. Okay, so now let's think about something here. Let's say that we have two things. We have this AB, which is 3, 7, and we have A prime, B prime, which is 2, 4. And we're interpreting them, the 2 and the 3, mod 5. And or mod, which one? Is that right? What are we interpreting it at? 3 times 15, 3 times 15 plus 63, mod 4, 15 plus 63 is, yeah. 15 plus 63 is that correct? Let's just see what's going on here. Okay, so 3 times 5 is 15. 7 times 9 is 63. 63 mod 45 is what? 18? Right? So 18 plus 15 is not this. So we're interpreting it as A mod n. So A is wait, what am I saying? Well, I got to do it the other way. What's 43 mod n, mod 5? 3. Okay, what's 43 mod 9? Mod 9. 7. Oh, yeah, that's it. So that's right. Okay, 22 mod 5 is 2. 22 mod 9 is 4. Okay, sorry. Okay? Okay, so this is the mapping. These two correspond. Let's do something. Let's add up the pairs. Okay, so that's what you get. 3 plus 2 is 0 mod 5, and 4 plus 7 is 9 mod 7. Is 2 mod 9. Okay? Okay. What about, what is x? Where x equals 0 mod 5 and x equals 2 mod 9. Okay? Okay, so that's what we got. So now we got this pair of numbers, and now we're trying to map it back to x. So let's try something. This was 22. The corresponding thing to this pair was 22. The corresponding thing to this pair was 43. And I added these pairs, and I got 0, 2. What if I added these two? What would I get? Okay, I got 65, right? Now let's take 65 as 20 mod 45. What is it 0 mod 5? Is 20 0 mod 5? Yes. Is it 2 mod 9? Okay. So it's an isomorphism in the sense that not only is there bijection between the elements of these two sets, these pairs of numbers, and these numbers mod mn, but these actions correspond. If you add in one system, it's the same as adding in the other system. You'll get the same elements. Okay? It's an isomorphism with respect to these operations. And if you add, right? If you add in this system, it's the same as adding to this system. You will get the corresponding movements of objects around. Okay, so you can work in either system. Okay? Okay, so that's what it's saying. Okay? Okay, so now that's the CRT and the the Fermat's little theorem. Let me give you a quick break, and then we're going to talk about public key cryptography. Okay. Okay, so, all right. So in computer science, we have these things called bits, true and false. We sometimes associate them with true and false. We have OR operations. When we think about OR, we think about either one being one, then the answer is one, and so on, right? This is what we have. And now we have something called exclusive OR. Okay, this is a fancy operation where if you have two ones, you get a zero. It means you have exactly one. That's why it says exclusive OR. Okay? If you do 1 and 1, you get a 0. If you get 1 exclusive OR 0, you get 1, and so on. You can think of it as also parity of the number of bits. If it's even, it's 0. If it's 1, it's 1. Okay, it's also modulo addition, modulo 2. It's exactly the same. You just take the remainder for 2. Okay, so there's one nice thing here. If you take A XOR B, you get A back. Okay? Like, for example, 1. If you XOR with 1 and 1, you get 1. And if you XOR 0 with 1 and 1, you get 0. Okay? And so on. Okay? Okay, so why is that good in cryptography? We're talking about cryptography, right? It's always good to get your message back, right? Does that make sense? This is this cute little idea, right? This is like, oh, look, I can just add B again in this system and I get back A. Okay, so it's sort of cute idea. Okay, so here's why is it doing that? Okay. I don't know. Yeah, it's LaTeX is a lot of stuff goes on in LaTeX. So, okay, well, it's still not going to go. Okay, there you go. Okay, so this is cryptography. So what happens is you have Alice and Bob and Eve. Okay, so Alice and Bob are trying to talk to each other, and Eve, I suppose for evil, is listening, right? And so Alice and Bob is A and B, right? Player A and player B. This is a cryptographer thing. So they can share a secret S. Let's say they could share a secret S. Okay? Like, those movies where they carry the secret codes in the briefcase or something. Well, you probably don't watch those either. So Bob has a message. He wants to encode it using the secret, and he wants to send it over to Alice, and Alice wants to decode it using the secret. This is sort of the old school coding. Okay? So here's an example. There's a one-time pad. Is you take a secret S of strength of length M. You share it. Bob and Alice know it. Nobody else knows it. That's a bit string. Okay? And say the message is some bit string. So what Bob does is he just bitwise ORs it. Exclusive ORs. Okay? And what Alice does is she bitwise exclusive ORs the message she gets. And it works because the message with the bitwise exclusive OR times the bitwise exclusive OR gives you a message back. Okay? Very cute idea. Right? Okay. Totally secure. You know nothing about the original message. If you know nothing about S, I showed you nothing about S. Right? So the Eve doesn't know anything about S, and she doesn't know anything about M. Each bit could be either a 0 or 1. It doesn't. If you think the message is a 1, the secret could be either 0 or 1, and it'll flip it or not. Okay? So it's totally secure. It leaks no information at all. The message is complete. It's a perfect scheme. Okay? Given any encoding message is any message is equally likely, right? If you give the encoding, you have this bit string, and you can't tell whether the original message was a 1 or a 0 if you don't know whether S was a 1 or a 0. Okay? It's a shared secret. You see this line up at the top? There's this line where they talk to each other. If they could talk to each other already, why are they just not talking to each other? Why do they need to encode? I don't understand. Is it just it takes longer time so you don't say anything mean or something? I don't know. Okay, it's a relationship hack. So uses up the one-time pad. What happens is over time, if you use the bits over and over again, information starts to get revealed. Okay? Like if I send 2 messages with the same one-time pad, then maybe they can figure out something. Okay? Okay. So, or less and less secure. So here's a different picture. And this picture doesn't have this line at the top. Okay? It's what you do with, it's Amazon and you. Okay? You never shared a secret. Amazon doesn't, you didn't talk to Bezos, right? So, but Bezos, what he did is he said, hey, here's this, public key. He just sends it out there. Says, hey, everybody, I'm Amazon, here's this key. Okay, whatever this key means. Okay? And what this key means is it says, here's this key and use this algorithm. So the algorithm is an encoding algorithm. So Bob uses this encoding algorithm of his message with this public key that everybody knows. Eve knows too. That's why it's in red. Everything in red, Eve knows. Okay? Well, except for M. Okay, M is not in red. She only knows the encoding of M and K. The encoding, not the arguments. Okay? So then it goes over there, and then Alice decodes it. All very, everybody knows the public key. Bob and Eve and me and you and everybody. Everybody can encode. Anybody can talk to Amazon, right? I can send a message to Amazon and it can make it encoded. That's what I want to do, right? I want to send my credit card to Amazon, because they want my money. But only they won't give me stuff without giving them that, right? So only Alice knows the secret key, though. That's the idea. There's this little blue thing here that nobody knows. Okay, but Alice. And somehow with that secret information that only she knows, she can decode. Is this even possible? Does this make any sense? This is just a mad, crazy scheme. Yeah. No, Amazon is Alice here. Alice knows. Amazon is Alice. Yeah. Yeah. In this scheme. I don't know. I haven't told you they exist yet, so maybe, yeah. Okay. So, okay. So, the public key. Yeah, the public key tells you everything that you need to know. Okay. So, is this possible? Does it seem surprising to you? How is it that everybody can know the encoding algorithm and only somebody who knows the secret can know how to decode? It's a little surprising, right? So is it even possible? I don't know. I don't know whether it's possible. But we do it all the time. So I don't know. I guess we think we're doing it, okay? We're using such a scheme, and I'm going to tell you the scheme we're using. It's called the RSA scheme. So here's how you do it. You pick two large primes, P and Q, very, very large, hundreds of digits, and you multiply together, and you get n, big number n, okay? And now you take P minus 1, Q minus 1, and that little P minus 1 in Fermat's theorem and that Q minus 1 in Fermat's theorem are relevant here. But let's just say for now, it's sort of just arbitrary. Just trust me. You take some E, like it's just a number, that's relatively prime to this expression, okay? P minus 1 times Q minus 1, okay? Now, since it's relatively prime, you can compute an inverse, mod P minus 1, Q minus 1. Remember we reduced by exponents in Fermat's theorem? We could reduce by exponents, and we need to reduce mod P minus 1. Something like that's going to happen. Okay? So this E minus 1, E inverse mod P minus 1, Q minus 1 is one thing. Okay, this is all private. Okay, so Amazon is doing this, or Alice. Then what Amazon or Alice says is, I'm going to announce N. I'm going to tell everybody this N, big N, which is P times Q. And I'm also going to tell them E, which is the encryption code. So that pair, N-E, is my public key. So I tell the whole world. I announce it. Okay, what didn't I tell the world? I didn't tell them P and Q, and I didn't tell them D. Right? Right? There's a few things that are running around. There's P and Q and E and D, and the product of P and Q. So I tell them the product of P and Q and E, but not P and Q. Yeah. It's not squared at all. It's just a footnote. Yeah. Okay, so it's typically small. Usually you use E to be 3. Okay? Now the encoding is you just take your message, you think of your message as some large string of 500 bits or something, or 500 digits. It's in your system. It's N is big enough to hold a number that long, okay? Because N is 500 digits, so mod X is some 500-digit message. You take it to the eth power mod N. Okay, that's the encoding algorithm. Okay? Now the decoding algorithm, what Alice does is she takes it to the dth power. She takes whatever she gets, which would be x to the e, and she takes it to the dth power. Okay? So the question is when you decode the encoded message, do you get back the message? It's not very good if you don't get back the message, right? Bob is trying to send M, so he encodes M. And then Alice wants to see what Bob sent, so she decodes it, so she could get back M. And how did he encode it? He took M to the E, and then Alice took what she got. What she got was M to the E here, and so she raises that to the dth power, which is M to the E times D, which is equal to M mod N, which we hope to be equal to the original message. The decoding of the encoding should give you the original message. Okay? So let's just do it. So we have to see. We'll prove it. But let's just do an example. Okay. So let's take a large prime 7 and a large prime Q. That was a joke. They're not very large, but you multiply them together. You told the whole world 77. They have no idea that the product of what P and Q are. Okay. Well, maybe. This is predicated on something, right? That we can't factor easily, right? Because if it's easy, if people had an efficient algorithm for factoring, then they could just break it right away, because they could just factor this. We didn't tell them P and Q, but we told them the product. If they could figure out P and Q if they could factor. Okay? Okay, so then P minus 1, Q minus 1 is 60. So I'm going to choose E equals 7 because E equals 3 is 0. It has the GCD of 3 and 60 is not 1. So now, but with E equals 7, GCD of 7 and 60 is 1. So we could do extended GCD. Oh yeah, look here, I'm doing extended GCD. This is the one I actually did before. So that's actually what I did before. I just did it the same way, right? I took the equations, and this is how, if you're asked to do this on your homework, you can just do it this way. It's much more convenient. You subtract the equations, 7 and 4. How do you make it smaller? You subtract, and then you get your result over here. Okay, so now what we have is we have everything. We have our P and Q, which we multiplied together to get N. We have E, which is our encryption exponent, and then we have D, which is our decryption exponent. Okay, which is negative 17, which is 43 mod 60. Okay, so now all I have to do, let me run it. So there's a public key, 77.7. The message choices, you're only allowed this many messages. Those are all the possible messages. So I'm going to send the message 2. I don't know. I feel like 2 is good. So the encoding of 2 is 2 to the E, which is 2 to the 7th, which is 128 mod 77. It's 51, right? So you can do this, right? Everybody knows that 2 to the 7th is 128, right? You double, double, double. 51 to the 43. Okay, so let's do that. Oh no. Yeah, I can do this, right? It's not fun, right? Okay. And not only is it not fun, if in general, this exponent could be a huge number, a 500-digit number. So it's really not fun, right? Okay, so I can't decode this, right? Taking this exponent is an expensive operation if you think of multiplying that many times. Okay? Okay, so how do we implement this scheme so we don't take forever? I mean, 43 for me is a disaster. 2 to the n for a computer is a disaster. 2 to the number of bits, right? 2 to the 500 is what it would take, or 200. Okay? So what we notice is 43 is this. And what are the numbers on the right-hand side? What do they look like to you? Are they powers of 2? Okay. So squaring has to do with powers of 2. If you square a number, what do you get? If you take a number, its exponent is 1. If you square, what's its exponent? 2. If you square it again, what's its exponent? 4. Now you get big exponents, right? Every time, if I square it, 10 times, I get 2 to the 10th in the exponent, right? So now you see how I can get big exponents, right? I can multiply, if I square things over and over, I can get large numbers in the exponents, right? So in this case, I'm going to write the number in binary, using the powers of 2. And I see that 51 to this is 51 to the 32 plus 8 plus 2 plus 1, right? And now when I have a to the 8, then I can split it, right? I can say that's equal to 51 to the 32 times 51 to the 8 plus, right? It's telling me how many I have. So I can spread them out this way. Okay? So now there's only 4 multiplications I have to do instead of the 42. Except not, right? I have to actually compute 51 to the 32 and 51 to the 8. Okay? So I need to compute these. Okay? But 51 to the 1 is 51. That was easy. 51 squared was this. That was less easy, but it's here, right? 51 times 51 is that number. You could mod it out. Okay? 51 to the 4th. I could either multiply 51 together 4 times, or what else could I do? 51 squared, which is 60 times 60, right? That's only one multiplication. Okay? 8, so on. Right? Okay, so now I've done it. How many multiplications did I do there? I did like 3 multiplications there. I can go, I still need to go to 32. And, every time I just square the previous number. Okay, so it's 5 more. That's 5 multiplications plus the 4. And then now I need to plug in. I get all these numbers. I multiply them together, and I get Oh, look, what did I get back? I got 2 back. That was what the message was. You remember that long time ago? We had this message, right? Way back here. We said, let's code up 2. 2 to the 7th was 128, which is 51. And now I'm taking 51 to the 5th to 43. What should I get back? 2. Okay, so I got back 2. Okay, so this is an advantage. It was much easier even by hand. It was easier. I did this by hand, right? Okay, at some point. Okay, so you can actually write a program to do this. So what you do is the following. What you do is you say, you're taking x to the power y, mod m, okay? If x equals 1, if y equals 1, y is the exponent, you just take x mod m, right? You just return the value, x to the 1 is easy. Otherwise, you take, you square x, right? And then you divide y by 2, okay? So that's like saying, what I do is I square x, and I divide y by y2, and then I pass in x squared, and I take it to the y over 2th power, intuitively. And that would be x squared to the y over 2, which is x to the y. Okay? Okay, so this is just the inductive proof, but that's what's happening. So what happens is x to the y here, what I'm doing is I'm taking the squared, taking x squared here, I'm using scheme again, let x be x squared, and then I'm calling power on the square, right? I'm calling this function again, on the square with the power 1 over 2. Now, y over 2 is not an integer necessarily, right? So you have to deal with the fact that it might be odd or even. So if it's odd, that's what this extra thing is. I either multiply by this thing or I don't. Okay? Okay? Last expression computed in the recursive call is this, right? This is this expression. That's this first part. Okay? And now y over 2 is integer division. And so now what we do when we come back, what happens is when we did y over 2, whatever we got back was the value to the y over 2. Okay? And now we square it, we get x to the y. Except we don't, because we floored it. So if it was odd, what we need to do is multiply by x again. So that's what this says. If it's even, I just returned what I got. And if it's odd, I multiply by x. Okay. Okay, so another way to do it is you just compute like we did, x1, x squared, x to the 4th, x, and so on. Okay, then I multiply together x to the I, where the log ith bit of y is 1. Okay? So 43, this is it in binary, and that was the first bit is x to the 1, the second bit is x squared, third bit is, the next bit that's on is x to the 8th, and so on. Okay? So, all n-bit numbers. Now, there's another good thing about mod. This is where mod is really important. Does somebody want to close those doors, maybe, out there? So, can somebody run out? Yeah, thank you. Okay, so if you didn't have mod n, if you take exponents, what would happen to the numbers? They would get huge. But here we're always modding down to n, big N. Okay? So we always are working with small numbers. Okay? So with repeated squaring, we're doing order n multiplications, and each time we do a multiplication, we're multiplying 2 n-bit numbers. So the total time is n squared. Okay? For each multiplication, the O of n cubed time. So this is efficient. We can get x to the y mod n. Thank you for closing doors. Yeah. Okay, so it takes O of n squared cubed time. So it's a little expensive, right? But 500 digits, you can do it. But it's expensive. I don't know whether they do anymore, but they made hardware to do this fast because it is expensive. In fact, they made hardware that did better than n squared time for multiplication because n cubed is still sort of a big number, but it's not 2 to the n, right? 500 cubed is something you can do. Okay? So, so modular arithmetic, exponentiation is pretty fast. It's all, so we can do all of this, right? We know how to, the only parts we haven't really figured out is how to generate primes. That's one part. But we can find the inverse, right? We can multiply them together, and we can encode and decode efficiently. Okay? Okay, so it's a few 100 million operations, so total. Easy peasy. Okay, so, okay, so now the decoding. One thing we have to do is we have to say this is true. When we take the encoding, which is m to the e, and we raise that whole thing to the d, we want to say m to the ed, to the exponent ed, right? That's how exponents work, right? You multiply them together, is equal to m. Okay, so that's what we need to finish. Okay? Okay, so let's see. Okay, so 2 minutes. I'm going to do this, what day is the day? Thursday. I'll do it on Tuesday. Yeah, so I'll finish off on Tuesday. Okay, so just for notes, you should remember from class today. Okay, what's the proof of Fermat's theorem? Right? You should understand what that proof is. It's a bijection, right? You take all the things and you multiply them by a number. You look at that bijection, and then then you have a nice inequality that you can prove. Okay? And then I'll let you go. Good. Yeah. It's a multiplicative inverse of 7. Mod 60. Oh, okay. Mod p minus 1, q minus 1. Okay. Right? Does that make sense? Yeah, I just follow the scheme. Mod it's the inverse of e. Mod p minus 1.
The inverse of e would be the exponent.
No, it would be d. The exponent depends on when you're talking.